So by the end of this video lecture, students will be able to relate reaction quotients, Q to K, and be able to express the direction with which the reaction needs to proceed in order to reach equilibrium. And you guys are going to look at a slew of equilibrium problems and basically various approaches using ice tables and equilibrium expressions and all of that good stuff. So we've already discussed K and basically how the size of K is going to dictate the predominance of products or reactants. In our previous lecture, we talked about how very large Ks are going to mean that products are going to predominate, and that very small Ks are going to mean that reactants predominate. Okay, so what I want to point out here, though, is that the size of K and time required to reach equilibrium are not directly related. Okay, so what I want you guys to understand or kind of refresh is that time for equilibration to occur is dictated by the activation energy. It's dictated by those kinetic factors that we discussed in the previous unit. Okay, so the larger your activation energies, obviously the slower your reaction. Remember that the forward and reverse reactions have to get to the same rate. So basically, the time for equilibration to occur or to be in that state is dependent on kinetic factors. Now, the size of K, okay, the relative shift, right or left, is determined by those thermodynamic activities that we've discussed very briefly in our previous lecture. Okay, so size of K and the time of equilibration is not going to be directly related. So I want you guys to just have that in the back of your mind. Okay, so we understand that K can tell us, the extent to which a reaction proceeds. Either we're going to have mostly products or mostly reactants based on the size of K. However, we can use something called the reaction quotient, which is Q, to tell us a few other things. Okay, so the reaction quotient Q can help us determine if a reaction is at equilibrium or if it's not. Okay? It can also help us decide which direction the system needs to move in order to reach equilibrium. Okay, so we're going to use basically a modified version of our equilibrium expression, and instead of using K and concentrations of our reactants and products at equilibrium, we are going to use Q to represent the reaction quotient, and we're going to use initial concentrations of our reactants and products to solve for Q. Okay, and then we're going to take our Q value and subsequently compare it to our K value, and that can answer a ton of questions for us. So when we go ahead and compare our Q and K values, depending on how they relate, that's going to dictate whether our reaction needs to shift towards products or shift towards reactants or basically remain the same. Okay, so if we go ahead and look at the first example where Q is less than K, in this situation, the initial concentration of our reactants is much larger than it needs to be in order to be at equilibrium. Okay, so in order for the system to reach equilibrium, more products must be produced. So the reaction is going to shift to the right, okay, and you're going to decrease the number of reactants and increase the number of products, and you're subsequently going to reach equilibrium. So that's the direction that reaction would need to shift. Now, if your Q and K are equal, you're at equilibrium, so no shift needs to happen. Conversely, to our first example, when Q is greater than K, that basically means that the value of your products or the quantity of your products in that initial situation is larger than the reactants. Okay, so in order for equilibrium to be reached, products need to be converted back into reactants. So your reaction is going to shift to the left, decreasing the number of products and increasing the number of reactants. So let's go ahead and let's do a couple of practice problems using our Q and K values. Okay, so the first thing we want to do is we want to write our reaction quotient expression. Okay, so notice I've written this expression with respect to initial concentrations, but I've written it very much in the same way that I would for my equilibrium expression. Okay, now I'm going to be utilizing the initial concentrations that they've provided in each of these problems to solve for Q for each one of these cases. I'm then going to compare Q to my K value that's provided here, and I'm going to dictate whether or not a shift needs to occur to the left or to the right. So let's go ahead and let's do problem A. So my Q value here, after I've plugged in all of these initial concentrations, is quite large, okay, when I compare it to K. So in this case, Q is going to be much larger than the K value that they've provided. So because Q is larger, that means that products predominate, okay? And so since products predominate in that initial situation, I'm going to need to decrease the number of products and increase the number of reactants in order to get my ratio to be the one that corresponds to equilibrium. So in this case, my reaction is going to shift left or towards my reactants. If we go ahead and we look at the Q values for these other two problems, okay, so for B, our Q value, if we plug in those initial concentrations, is 0.60. Okay, so in that case, Q is equal to K, so we're at equilibrium, so there's no need for a shift. In the case of C, we're going to get 0.002 as our Q value. So in this case, Q is smaller than K. Okay, so our reactants, or excuse me, our reaction is going to need to shift to the right or towards our products in order to be in equilibrium. Okay, so this is how we utilize the reaction quotient to figure out what direction our reaction needs to shift in order to be at equilibrium. So now let's go ahead and look at some equilibrium problems and the various approaches that we may need to take. For this problem here, we're going to look at a very basic equilibrium calculation. This is actually pretty intuitive. You probably would be able to do it after the last lecture, but we're going to go ahead and go through it here. So in this context, guys, they've given us a balanced equation that's going to allow us to write our equilibrium expression. So the equilibrium expression is as follows. Notice I've written it with respect to Kp. They've given us information regarding Kp as well as partial pressures. So that's why I've written it in this manner. Okay, so we have a balanced equation. Now we could go ahead and write out an ice table, and we're going to go do that really quickly. And I'll point out what's really necessary in this problem. So now that we've written out an ice table, we're going to go ahead and look at what they provided us and decide what was really necessary from this portion of the problem. Okay, so in this context, guys, they have told us that this is our Kp value, and they told us that in our equilibrium mixture, we have a partial pressure of our H2 of 0.982 and a partial pressure of our N2 at 0.432. So basically what they've given us is the equilibrium value of N2, H2, and they want us to solve for the equilibrium concentration of NH3. All right, so basically the use of the ice table is not really necessary in this specific problem. However, I just want you guys to get used to differentiating between initial, the change, and the equilibrium. Okay, so let's go ahead and let's plug in our equilibrium values that we know. So we have our equilibrium values plugged in, okay, and then we're going to take these values and plug them into our equilibrium expression. We've also been provided our Kp, our equilibrium constant, so we're going to go ahead and plug that in as well and solve for x. So now that we've plugged all of these in, we're going to go ahead and get x squared all by itself. Okay, so cross multiply up, and that's going to give us, okay, so now that we have x squared, we're going to go ahead and take the square root of both sides, and our x value is going to equal 0.002435, and that's going to correspond to the concentration of our NH3 at equilibrium. So these are the steps you would take to solve a basic problem like this. So in a problem here that we've been provided, we've been asked to solve for the concentration of our reactants and products at equilibrium. We've been given initial values of the concentrations, or at least the information to solve for the concentrations of our reactants. And we're subsequently going to follow the protocols that we've done in the past. So we have our balanced chemical equation, and that's going to allow us to get our equilibrium expression. So now that we've established our equilibrium expression, we're going to go ahead and set up our ice table. So now that we've established our ice table, we want to plug in the variables or the values that we actually know. So if we go ahead and we look here, they told us that we have a 1 liter flask and we have 1 mole of hydrogen and 2 moles of iodine respectively. Okay, so these values, notice the moles and the liters, are obviously not molarity, which is what we need here, but we're going to go ahead and find out those values. Okay, so we know that we have 1 mole of hydrogen gas per liter, 1 liter, and that's going to give us 1.0 molar as our concentration of H2 initially. Okay, in that same way, we're going to do the same approach with the hydrogen. okay, and that's going to give us 2 molar. Okay, and then obviously HI is not present yet, hasn't mentioned any of it, so that's the assumption we're going to make. Okay, so now our next step, guys, is going to revolve around the change associated with each of our reactants and products. Okay, so we know that hydrogen and iodine are decreasing in concentration, and HI is increasing. Okay, so negative X, and plus 2x are going to be the relative changes of each of those items. Notice, again, we get this 2x from the fact that the coefficient is 2 in front of HI, and the minus 1x and the minus 1x corresponds to the decrease in the concentration for H2 and I2 respectively. Okay, so now we can go ahead and figure out what our equilibrium concentrations are going to be relative to our initial concentration. So now that we have each of our equilibrium values, we're going to go ahead and plug them into our equilibrium expression. And the reason why we're going to be able to utilize our equilibrium expressions is because they've also given us our equilibrium constant. Okay, so we're going to go ahead and plug all of these into the above, as well as our equilibrium constant, and solve from there. Okay, so I've gone ahead and plugged in all of our equilibrium values that we've established in our ICE table into our equilibrium expression and set those equal to our K value. Now, I do want to point out, guys, here, notice I've dropped the 0 here. That's obviously a redundancy, so that's why I have only 2x there. Also, guys, please understand that the squared value here applies to everything that is inside the brackets, okay? And so the 2x is being squared, not just the x. So now we need to basically apply all the algebra that is basically being represented here and set this up in order for us to be able to solve for x. Okay, so we're going to go ahead and square this and FOIL this out, and that's going to give us the following. Okay, now that we've established that, we're going to multiply up here, all right, and then get everything to one side of the equal sign. That's going to give us, so now that we have this equation here, it's very apparent that we're going to need some sort of additional help in order to find what x actually is. So in this case, we're going to utilize the quadratic equation, where x is going to be equal to minus b plus or minus square root of b squared minus 4ac all over 2a. Okay, and so remember, this is our a, this is our b, and this is our c respectively. And when we solve using our quadratic equation, we're going to get 2 answers. Okay, so in this case, if we go ahead and do that math, I'm going to do that off to the side here, you're going to get one of 2 answers. So the 2 answers that we obtained using the quadratic equation are each of the following. Okay, now when it comes to these problems, we want to make sure that what we are solving for, or what we're establishing, actually makes sense with respect to the original problem. Okay, so if we notice our largest initial concentration is 2 molar. Okay, so if x equals 2.323, what that would be indicating is that we are losing more iodine than is actually present. So in this context, we know that this is not a valid answer, and so this one is going to be the x value that we're going to use. Additionally, let's say you got a negative x value. There's not going to be such thing as a negative concentration, so that would be another value that you knew you could drop off. Okay, so this is my x value for this problem. Now we need to establish the concentrations of all of our iodine and hydrogen and hydriodic acid at equilibrium. Okay, so we're going to go ahead and we're going to take this x and plug it into each of these values here. So we've plugged each of these into the equilibrium slots here, okay, and those are subsequently given to give us the following answers. So now that we have these answers for our concentrations at equilibrium, we can actually check ourselves by plugging back into the equilibrium expression and comparing that to the Kc value that we were provided. So we're going to go ahead and calculate the concentration of our reactants and products at equilibrium when given our initial concentrations of our reactants, as well as our equilibrium constant in a balanced equation. Okay, so we're first going to start our problem out by writing our equilibrium expression. So we have our equilibrium expression here, and what we're going to go ahead and do is we're going to now set up our ICE table so that we can figure out our values for our equilibrium concentrations. So we have our ice table here, okay, and then now what we're going to do, guys, is we're going to go ahead and we're going to plug in our initial concentrations, calculate our change, and our equilibrium values to plug into our equilibrium expression. Okay, so much like we've done in the past, we've plugged in our initial concentrations. We're going to now establish the change associated with each of our reactants and products, okay, and this should be familiar at this point. And then we subsequently go ahead and figure out or write out what our concentrations at equilibrium should look like. Okay, so now that we have these values here in the equilibrium row, we can go ahead and plug them into our equilibrium expression. So what we'd normally do with our problem here is we would go ahead and FOIL out the bottom, cross multiply up, distribute this squared across what's inside the parentheses, get everything on one side, and use the quadratic equation to help us solve for our x value. But what I want you guys to notice is that this example problem here is actually a perfect square. Okay, meaning that I can take the square root of both sides of these to cancel things out. Okay, so another way to look at this setup here, especially the bottom, is as the following. Okay, so notice we have something squared on the top as well as something squared on the bottom. Okay, so basically what that means is I can simplify this by basically taking the square root of both sides of this problem. Okay, and what that's going to give us is the following. Now, if we go ahead and distribute, cross multiply, and solve for x is going to end up equaling 0.160 molar. Okay, so this is our x value. We're now going to take this x value and plug it back into our equilibrium value. So plug that x in and solve for each of the concentrations of H2, and HI. Now that we've done that, we have our various concentrations at equilibrium of each of our reactants and products. We can then take these values to check our work, plug them back into our equilibrium expression, and we should be able to get a value very close to our Kc. So basically, with the perfect square situation, it's something you want to look out for. It is something that comes up pretty frequently on the AP exam, so you want to make sure that you're comfortable with it and that you can spot it to basically save yourself some time. Otherwise, you're going to be using the quadratic equation, taking a whole lot more time on the test than you need to. So in this problem here, we're going to deal with special situations in which we have a very small k, and the mathematics associated with the problem end up being somewhat problematic. So basically, same steps we've been doing. We're going to set up our equilibrium expression, we're going to set up our ice table, plug in our concentrations, and work from there. Okay, so we've set up our equilibrium expression. We're now going to go ahead and set up our ice table. Okay, so what they've given us here to plug into our ice table is the initial molar or mole value of our product, or excuse me, of our reactant, and the total volume of the flask. They've made no mention of our two products, so of course we're going to assume that those are both going to have zero concentration in the initial point. Okay, so in order to calculate our molarity here, we're going to divide our moles of NaCl by our 2 liters, and that's going to give us 0.50 molar, okay, concentration as our initial value. So again, as we have in the past, we're going to go ahead and set up our change. Okay, so we're going to be decreasing our amount of reactant. Normally we've had this as just x, but it's going to be 2x in this situation because of the coefficient of 2 in front of the NaCl. Okay, and we're going to have plus 2x for our NO and plus x for our Cl2. Okay, so we have each of those respectively set up. We're going to go ahead and set up our equilibrium, okay, as we have in the past. Okay, and then these values are all going to be plugged into our equilibrium expression. So we've gone ahead and plugged in our values from our ice table into our equilibrium expression. And what you guys are hopefully going to notice is that very quickly we're going to end up with a cubic function here. And that's going to cause quite a bit of problems with respect to solving for x. It's less straightforward and basically will require a lot more work. So something that we can do or attempt to do is a simplification process. And this process only works when our k values are very small. Okay, and what we're going to do is we're going to basically drop the x value from the reactants. Okay, so the reason why we are able to make this assumption or try this is because a very small k means that reactants are going to predominate, right? Okay, so a very small k means that mostly mostly reactants are present. So really the change in the concentration of our reactant is going to be relatively small. Okay, and because of this, we are going to go ahead and just ignore the X component of the reactant's change. So when we go ahead and do that, the expression that we get is going to look like the following. Okay, so now that we have the expression with our 2X dropped from the reactant, we're going to go ahead and solve this like we normally would. So we go ahead and cross multiply, divide out that 4, and we end up with x cubed is equal to 1.0 times 10 to the negative 6. Okay, if we take both sides and raise it to the 1/3, we're going to end up with x equaling 0.01. Okay, so now we need to always check and make sure that our calculation for x is an acceptable value. In order to check x, we are going to take our x value and compare it to the original concentration that it would have been subtracted from. Okay, so we're going to take our 0.01 divided by 0.50 molar. Okay, and then we're going to multiply that by 100, and that's going to give us 2%. So as long as your x value is 5% or lower than the original concentration value, you can use this approximation method. Okay, so x is valid, so we can therefore go and plug it into our x species that we see along the equilibrium line here to calculate our various concentrations. So when we plug these values in, we get these various concentrations utilizing this approximation method when we have a small k.